This is going to be a fairly short video because domain and range of linear functions is fairly straightforward. If you have a linear function, so some f of x equals mx plus b, essentially you can plug in absolutely anything for x. Also, you can have absolutely any output for y. So here I just included some graphs of the three types of linear functions we would see, and actually I should even have these arrows continuing on forever and ever. So increasing function, decreasing function, and then the constant where it's a horizontal line. The key is if we made the domain for these, we could see for every single one, x is defined absolutely everywhere. And for y, same thing, defined absolutely everywhere. So if you have a linear function without any other restraints on it, the domain is going to be all real numbers. So you'll have negative infinity to positive infinity every single time. And range will be negative infinity to positive infinity every single time. So that's the punchline to domain and range of linear functions. However, something I do want to bring up here is what if we're working in a word problem? Because there could be certain real-world pieces that change the domain. Even if it's a linear function, there might be constraints on it. So let's look at this example where we have a phone company charges for service according to the formula C of n equals 2.4 plus 0.1 n. So I'm just going to write that down off to the side. And what we have is that n is the number of minutes. I'm just going to make a note that n represents the number of minutes talked, and C of n is the charge, the cost in dollars. So what is a good domain and range for the function? So this is a linear function, so if I graphed it, I could technically graph it absolutely everywhere. However, can we talk negative minutes in a month? No. We could not talk at all. We could have 0 minutes, but that would be the minimum for it. So what we're going to see for n is that it has to be more than or equal to 0. Now, you could leave it like that, and that's great. But we could think even a little bit further to it. It's like, well, then what's the maximum number of minutes? Are we limited there? And technically, we are. There's only so many minutes in a month that we could talk. So there is kind of this idea of a maximum bill. I mean, there's issues with this because we have to sleep. Like if you stayed up all month talking, there are issues with that. So we can just leave it like that. And it has to be more than or equal to 0. But something you could think about is a maximum, and it would be the total number of minutes in a month. But then there would be the argument that it would be impossible to talk on the phone every single minute in a month. So that's where I'm going to leave it off. But that could be an idea in a future word problem where there is this maximum limitation. Now, what this means for the cost is what we can see is what's the cost that lines up with this idea of 0 minutes. What's this minimum cost we're going to be seeing? So with that, we could look at C of 0. So if we plug in 0, what we're going to see is this cost of 2.4, and the units there are dollars. So we have this minimum charge of 2.4, and then from there it's going to increase because we have a positive slope. So C of n is going to be larger than or equal to 2.4. So it's kind of like there's this base charge for having the phone each month, and then it increases based on minutes. So that's what we could do to make a sentence here, is that the number of minutes talked will be at least 0 minutes. with a minimum charge of $2.40. Yeah, what we could do is find that maximum number of minutes in a month and then find that maximum cost. I believe I did a calculation on the side, and it's something like $4,322 charge for talking every single minute in a month. But that's just so extreme, and it's not a likely scenario. So we can just deal with this idea of minimum values for our input and output.